welcome everyone to this third webinar of all the aspects of debugging with PLS tools with the Universal Debug Engine. And in this webinar today, I'd like to show you or introduce Multicore debugging of ARM Cortex-A and R based SoCs. So yeah, my name is Jens Braunus. I'm Product Marketing Manager at PLS Development Tools, and PLS is a German-based company. We are located in the eastern part of Germany near Dresden. And since 1990, so 30 years, we are developing and manufacturing the debug, test, and trace tool Universal Debug Engine. Okay, let's start with today's webinar about multicore debugging of Cortex-A and Cortex-R SoCs. This is the agenda for today. For those of you who attended the last webinar 2 weeks ago, where I focused on the Oryx world, something is new, but also there are some things that I have told you already. For example, about the creating of the debug session and also about some multicore debug functions. But let us start with the first part of this webinar, the UDE workspace. If you want to create a debug session with UDE, you have to create a workspace. So the workspace is a file that contains all the settings, all the setup of windows and views, and all the things that you need in your debugging session or in your daily work. So this workspace is a file, as said before. It can be transferred to other PCs and also provided to other users, and provides you the ability to start again your work where you left off. So all the things that you need for debugging, you specify, set up only once, and then you can use it forever. This is the first step if you want to debug a multicore application, to create a workspace for that. So what you need to do is you have to define at first what target you want to debug. The controller type, for example, the debug interface that you want to use, which cores you want to debug of a multi-core system. It's sometimes not necessary to have all the cores available in the debug session because your application don't use all the cores, for example. And you have also, so sometimes you need also set up the target system, your controller, to be ready for debugging. Sometimes you have a watchdog which prevents you for connecting your target for a debug session or something like that. And you can use some init commands provided by the target configuration to disable, for example, the watchdog. All these things are all these things to set up is part of a setup guide in our user interface that helps you easily create a workspace. Also, you have to select which target device, access device, from our series of access devices, the UED2 Pro to Next or 3 Plus, you want to use, and how you want to connect to these devices. You have the possibility to connect using USB or even using Ethernet if it's in a part of your local network in your company. So once you collected all these information, then you can create the workspace file and connect to the target. And then finally, you have to load the binaries, the application that you want to debug, provided either as an ELF file together with all the debug information that the compiler provides, and in other cases only a hex file or a combination of hex and ELF file, which is then loaded into the target internal flash memory or into the target internal RAM. And finally, you open some windows which presents you important information about the application, for example, variables, registers, of course, the source code, and so on. Okay, then let me show you how it works. In the first part of this webinar, I use a Renesas R-Car device for demonstration. This is a picture of the hardware setup that I use. It's on my desktop here. I use a UAD2 Pro device for the target connection. That device is connecting using a USB to my PC and to the running software debugger, to the user interface of the debug tool. And I use a starter kit board from Renesas with an R-Car H3 device here. And this board is connected to the UAD using a SWD debug connection using our SWD and JTAG combined adapter here. And this is the only target-specific part of the whole setup, of the whole debugger setup. The debugger device, the UAD2 Pro, can also be used together with other architectures like Power architecture or AURIX or Infineon tri-core devices without any changes to the hardware itself. Only the adapter is target-specific here. Okay, the software architecture of the example is split in two parts. The first part is a multi-core application called Multicore Demo, which runs on the Cortex-A cores of this 8-core R-Car device. This device here has 4 A57 cores and a core complex of 4 A53 cores, and then in addition a real-time core, a R7 core, which is a 32-bit core, and all the A cores are 64-bit cores. The application itself is compiled in ARCH 64. That means it's a 64-bit application, and it should be loaded into the external flash of that device. And that results into the need that this application has to be copied from the external flash to the internal memory of the device by a bootloader that we have to provide. So this means that the start address of the Multicore Demo application, which is given in its ELF file, it's not valid at the boot time. And it's the first thing that you need to know when you set up a debug session. The application itself is compiled in a hex file and in a separate ELF file. The hex file provides only the binary for flash programming, and the ELF file only provides debug information. So you need both files for debugging this device. For the Cortex-R7, I have another application. It's called Time Demo, which is a single core application, 32-bit, using the ARM v7R instruction set or architecture specification. And the binary of that time demo is linked into the hex file of the multicore demo. So it is provided as a array, a binary array, and has to be copied to the R7 RAM. There is a separate ELF file provided or created by the compiler to provide debug information for the R7 part. The reason for that is that the compiler or the compilers are not able to combine 64-bit and 32-bit code or debug information into one ELF file. So we need two ELF files, one for the Cortex-A cluster and one for the R7 cluster. And this software architecture makes it necessary that we do some presettings and additional setups after we create a debug session from scratch. Also in that example, I like to reduce the visible cores. That means we want only debug for a Cortex-A cores and only the R7. In some, these are 5 cores instead of 9 cores that we want to debug. The reason for that is that 9 cores would need some more space on the screen than the selected 5 cores here. But the application itself runs on all the cores in parallel. Okay, then let's jump to the UDE to create a workspace. For creating a workspace from scratch, I use the file menu, select new workspace, and browse for a location, a folder. I use this pre-selected one and give the workspace a name, for example, R-Car demo. And then I will be asked to provide a target configuration. You can do it from scratch using the new button, or it is much more easier to use a default target configuration. We provide a huge set of predefined target configuration of almost all evaluation boards for the targets that we support. You see a list of the target the target architectures, beginning from all the ARMs, then some Cortex power architecture, tri-core, Oryx, and so on. And we have here, for example, the R-Car, the H3 starter kit here with 2 possibilities to connect using SWD and booting from the A57. That's what we want to use, or booting from the R7. So in this application, or this in this task here, or in this session, I want to boot from the A57 core. I select this, ready, then choose a folder where the target configuration should be saved. Save it. And from here, I can start it, or I can do some changes on the target configuration if needed. Open that, and then you have different possibilities, for example, to set up the device, the UID device to connect, and something else. But I can leave it in without any changes here. Press OK, and then I will be asked which cores I want to debug. I said before, we have 9 cores available, but we want to limit the number of cores in this debug session to 5. I deselect these 4. Okay, and then press OK. So then we get connected. We get some green lines for all the selected cores here. And then I told you that we need some presettings before we can load the application. The first presetting we have to do is to tell the debugger that he should not use the start address provided by the ELF or the hex file. So we open the so-called target interface setup. You can do it also by using the menu here, target interface. And then we have several setups here. We go to the setup page for the Cortex-A and set or check this box here, use hardware reset mode. That means that the target is set to the reset vector address after the reset, and from there a boot ROM code is executed, which then calls a boot header application located in the RAM, and this boot header application is copying the actual Multicore application from the external flash memory to the internal RAM. Okay. Then we need to enable the flash tool. That is done by add-in components. You have a list of available add-in components, and we need to check the flash tool. But in this case, it is necessary to do so because the external flash is sometimes available and sometimes not. So the flash tool is not automatically enabled by default. So we have to enable that and go to Tools, Flash Programming, and we have here the hyperflash of that device, external hyperflash available, and we should enable that. Okay, then we can program the flash. Exit. So now it's time to load the application. We go to File, Load Program, and browse in all the necessary hex and ELF files. So the part for the Cortex-A cluster is located here in this Multicore demo folder. And we have two hex files here. The first is the boot header, and the second is the Multicore demo hex file. At first, we need a boot header. Double click, and then the Multicore and Multiprogram Loader window gets opened. You see here the file, the hex file that should be programmed. The target location, we program it for the master core of that device. The master core is responsible for waking up all the other cores. You see only the cores that we have selected during the creation of the debug session. And for that, we have no other information. We have no debug information, etc. So all things are grayed out here. So only the first checkbox for loading the binary into the target is checked. Then we add the application hex file. We want to flash it, and we want to load debug information that is provided by a separate ELF file. So we check this box, combined hex ELF load. That means the name of the hex file is used to look for a ELF file with the same name, And this ELF file can be then used to provide all the debug information to all the cores. That means to all the core debuggers. A core debugger is a component in UDE which is responsible to communicate with a specific core. So we have core debuggers for the Cortex-A 57 cores, and we have core debuggers for the A53 cores, and we have core debuggers for the R7 core. So we check the symbols checkbox here to provide the debug information to the Cortex-A cores. And then we need also the simple information for the R7 core. So I look for the ELF file of the time demo. The ELF file provides only the debug information, no binary, because the binaries, I said it before, are linked into the Multicore demo hex and are part as a, or provided as a array of bytes that are copied to the R7 memory. But we need the debug information to show the source code variables, etc. So I check debug information for the R7 core. And then I press OK. And automatically I ask for providing the source files, because the application is not compiled at the same place in the same folder as it is provided to the debugger. The ELF file and the debug information contains the absolute path to the source file, and the debugger can't find this and asks for this reason for the source file. So he needs for the A core the main C, so I browse in the main C. Then automatically the Flash tool gets opened. I program all. And I can then start the application running. Okay, we browsed in the main C manually. That would be very annoying if you open another file and then another file, and every time you have to browse in and go to the source code location and so on. For that reason, UDE provides a mechanism to replace paths that UDE finds in the ELF file by the paths where the source code is actually located on your hard disk. For that, you go to config, select debug server configuration, look for the source code windows, and you find here two buttons. One is the aliases. There's one alias already available. That is the main C that we manually browsed in. You can delete that or you can leave it. But for the other files, we want to do a path replacement. We add a replacement here. This is provided. These are the information provided by the ELF files. So we select for the Multicore demo application the source file location, and then we are looking for the source file folder where the debugger should look like in this debug session. That's that one. And the same we can do also for the Cortex R7. Where is it? Here. Okay, and then okay, And then if we browse in, for example, main C or for the R7, for example, the main C, then automatically UDE replaces the path, looks at the right folder and open the file. And now you have a debug session. You can open some new windows, for example, not that one, for the first core, for the green one. It's much easier to call it by the color here. Every core is colored here, and you see also on the windows that all the windows which are core specific are colored by the same color. So the green windows belongs to that core, and the pink belongs to the R7 core, and so on. And maybe for the green core, I select that, I click on this button here, then you see here the core is changing, or on the status line, I can switch all the cores and see which core is the active one for the debugger. Also the run control buttons are working on only for the active one. So I can break, for example, here the core and make it go again. And then I can open, for example, a register view, browse for example, a GPIO register, which indicates, for example, the running state of all the cores. You see it's there are bits set and reset here. Each core is responsible for one of these bits here, and you see everything is running. Okay, then let's move forward and sum up the first things which are important here. I think the most important thing is how to use the Multiprogram Loader for that application. We have used 3 files, 2 hex files providing binaries. The first binary is the boot header located into the RAM, and the second is the Multicore demo binary, which is flashed to the external flash memory. And then we provide also a ELF file for the R7 application part, which only provides the debug information. The binary for this application is part of the Multicore demo hex file. Okay, so you have to select on the blue checkboxes where to program and what to program, and the green checkboxes where to distribute the debug information to which of the core debuggers. And in the case of the Multicore demo hex, we have also provided a ELF file, which has the same name as the Multicore demo hex, and automatically provides the debug information to the Cortex-A cores. Okay, then let's do some multi-core debug functions. We use the same target configuration, the same application, but I prepared a workspace with some more windows. So I opened that workspace. So this workspace can be saved, okay, and can be used whenever we want, but I use a more complex and more complete workspace here. It's the same workspace. We have the same application, the same settings for the Multicore and Multiprogram Loader. Press OK, then the Flash tool gets opened. I'm quite sure that that is the same application, so I can verify that without reprogramming it. exit, exit, and then this window is not important, okay, and then I can start the application. So you see everything is running. We have some variables that are updating periodically, and we see, okay, this is a good indication of the core states. So if I set a breakpoint, for example, in the R7 core, we have here a timer function or some code that realizes a clock with incrementing seconds, minutes, and hours variable, and we set a breakpoint here right on this line. Then you see, okay, we hit the breakpoint, and immediately, and all the other cores are stopped as well. So you see, okay, all the Cortex-A cores are stopped, and the R7 core are also stopped. Sometimes it is, you do not wish to stop all cores if you hit a breakpoint in one core. Then you have to tell the debugger that he should decouple the synchronization of the several cores. That can be done using the Multicore Run Control configuration. The Multicore Run Control configuration contains so-called Multicore Run Control groups. And you see here by default, this is given by the target configuration, all the selected cores are part of the run control group. But we want to independently debug the R7 core, so we move this out of this group so that we have a group of the Cortex-A part of the controller and the, or the SoC, and we have a R7 part of this controller. The master core, which is in this case the Cortex-57 core 0, have to be always part of the run control group. So this is this setup here is the only way to split the Cortex-R core from the Cortex-A cores in terms of synchronized run control. Okay, then let's press OK. Then we can start, for example, here the Cortex-A's. I click on the toolbar and select the Cortex, the green core, start this. You can see, okay, everything is flickering. You see here the register bit 13 is not updating. This is controlled by the Cortex-R7. If I start the Cortex-R7, disabling the breakpoint, then you will see, okay, now it's updating. You see the R7 is running. If I set the breakpoint again, then nothing is updated here. And also here, we see the indication of the running state of all the cores. Start this. And then if I set a breakpoint, for example, in one of the Cortex-A cores here, let me look for a good, we have also a clock here, and we can set a breakpoint also on this line. And you see we hit the breakpoint here, and at the very moment, all the A cores are stopped synchronously. Here you can see that the R7 is running, still running. The update is disabled at the moment because of the peripheral register window here. This is a core specific for the green one, so it's not updated. So you can see here only on the core state that it is stopped. Okay, then let's disabling, okay, and then you see we hit the breakpoint here again. If you want to put back the Cortex-R core to the run control group, then you have to stop all the cores. It is only possible to change the run control group settings if all cores are stopped. So we manually break here the Cortex-R cores, and then we can open the Multicore Run Control group and put it back to the group, and then disabling the breakpoint. Then you see if all cores gets running, and if I set the breakpoint here again, then also the R7 gets halted synchronously. Sometimes, or very often, you have shared code in your application. For example, we have a function which is called update signal, which I know this is a shared function and used by all the Cortex-A cores. If I set a breakpoint here, for example, at the very beginning, and run, then we hit the breakpoint as expected here in the green core, and then I start again and start again, instead start again. And I'm wondering why I don't stop at any other core. I'm very sure that the update signal function is also executed by the blue cores and the dark green core here, but it is not hit. The reason for that is that every breakpoint is core specific. So now maybe you think, okay, then I have to find the same function update signal into the blue one, go in and set the breakpoint, and then okay, now I stop also at the second core, not only on the first one. But if you have 3 cores, 4 or 9 cores, and want to set a breakpoint there, it would be very annoying to do this for every single core. So in this case, or for that, UDE provides a so-called Multicore Breakpoint, and you can use this already set breakpoint in, for example, in that green core here, to set this, or to check that should be a multi-core breakpoint. Okay, check that. Okay, then it is has another icon here, and you see it is a group of breakpoints for all the Cortex-A cores, not for the Cortex-R core, because this function is not part of the code of the Cortex-R, so it is recognized by UDE. Okay, there is no breakpoint here that can be set. And if I start the application, then you see, okay, we stop in the green one indicated here in the status line as well. And then we are here. This is the dark, this is the more blue one. And then here the dark green, and so on and so on. That is the concept of a multi-core breakpoint. You can also set the multi-core breakpoint directly. I removed that here. For example, if you want to set a breakpoint, you can remove that and that as well. And then I can set, for example, the breakpoint is here, set a multi-core breakpoint. But this is not a shared function. Let me show you that under update function. Okay, insert and remove a multi-core breakpoint sets instantly a multi-core breakpoint. Okay. Yeah, that is the part for setting a debug session for a multi-core application. and how to debug a Multicore application. What can you do with that? You have seen that this is quite easy to set up a debug session, flash a program, also with multiple ELF files, with multiple hex files. You have seen how it looks like to debug a Multicore application in one user interface. So you don't need to open separate debugger instances for each core. All the core specific windows are colored. That gives you a better overview of your application. And then I showed you synchronized debugging, including Multicore breakpoints, synchronized braking, stepping, and go. And yeah, that are the basic functions for Multicore debugging with UDE. Then I like to give you a very brief outlook what you can do with trace for Multicore system. For that, I use another board. This is an S32V processor from NXP. That is connected to a UD2 Next, which is not on my desk. It is in our company network somewhere, and I use the Ethernet connection for that. We have a JTAG interface, or is at that SWD interface here, and also a connection to the trace port of that device with a plug-in module to capture the trace information into the device trace memory. We provide 512 megabyte here in this device. And what you can't hardly see is the trace adapter here. It's a bit dark. So I open a new workspace, or a already prepared workspace for that. And this workspace connects to the UD2 Next in the network. I provide a IP address for that, and we load an application which is quite simple and it's not flashed. It is located in RAM. If I start this application, okay, I hit the breakpoint, and from there I want to start the trace. So I show you very briefly the configuration of the trace. You can open the trace configuration window, and then you see several tabs for each trace client that is provided by the board. A specific tab and a general one where you select, okay, which device you are connecting and what size of trace memory you want to spend for the trace recording. In this case, to save time, I use only 1 megabyte. And then you have a trigger setting. That means, okay, if you provide a trigger condition in trace, so for example, execute a specific function in trace, then you can provide a trigger setting and then trace from that condition until the trace memory is filled completely. We use this trigger condition as a so-called pre-trigger, so starting trace from trigger, and then we trace only the first 2 cores here. We do a program trace. We want to have some timestamps or timing information available to calculate or to analyze the execution sequence of the functions and, for example, do some time measurements. And we want to trigger at a function called worker O. Okay, then press OK, and then start the trace, start the application. And the trace has stopped automatically. The trace buffer was filled completely, and we see here, okay, we have 2 cores traced, and we see on the colors that, and here indicated by this column here that we have instructions, executed instructions recorded from core 00 and core 01. Then we can, for example, start the trace analysis to provide you a execution sequence chart. And this takes a while, so in the meanwhile, I can explain you a little bit more. The window here on top, you see the timing information, and you see that for several trace lines or trace messages, the time is always the same. The reason for that is that we did a branch trace. That means only branches are recorded, and every other instruction that are executed between the branches, every sequential instruction were reconstructed by UDE. So UDE assumes, okay, these instructions here belongs to this branch, and tells you this by the same timestamp. There's no possibility to do it more exact in this case here. Okay, and then you can, for example, go to the trigger position. Okay, that is our trigger position. There is something executed before, or something recorded before, but the interesting point here is the trigger. And you see, okay, here we now have the executed worker 0 function here, and then some other stuff on the other core. And if you look at the timeline, oops, why we don't see anything at the moment? Okay. You see something done before the trigger, and then we can zoom in using the mouse wheel, and you see, okay, worker 0 is called, and then worker 0 calls worker 1, and so on. What you see here, you can now set some markers here for do some time measurements. See the difference here on the bottom line. What you also see, and that is unfortunately sometimes the case for trace-based debugging or trace-based measurement, that we have some broken messages in between. These are the gray dotted lines here. And if you look for a broken message here, yeah, I did that before. So it is already filled. Then you see a broken message caused by a overflow of the trace system. So there were too many trace messages generated and could not transferred to the internal buffers and to the trace interface. So sometimes you have these broken messages here. But if you limit the amount of trace information a little bit, then you will be happier. So that is what I'd like to show you today. We have also a webinar on trace-based debugging and measurement that will be, I think, held in June or beginning of July. So there I will go more into the other things that you can do with trace. So let's sum up. Time is up. What I have shown to you, I've shown you how to set up a debug session, a workspace with UDE, and load the target application. then we did some basic multicore debugging of this bare metal application. I showed you the user interface and how to use synchronized run control and how to use the Multicore Run Control group, and what Multicore breakpoints are. And then finally, we did some very brief introduction into the trace support of UDE for Cortex-A and Cortex-R devices. Okay, thank you very much for your attention. And yeah, if you have any questions, then please use the webinar panel to ask or drop us an email, and we will answer these questions offline.